Let's understand probability in this video. Have you ever wondered how likely an event is, like drawing an ace or getting two heads in a row? Probability tells us how likely an event is, as a number from 0 to 1, where 0 means impossible and 1 means certain. A simple rule is PA plus P not A equals 1, which means either A happens or it does not. Odds in favor of an event compare success to failure. For example, odds 3 to 1 means 3 chances to succeed for 1 to fail. In sets language, if event A is inside event B, then PA is less than or equal to P of B. That is, bigger sets have bigger or equal probability. For any two events, the probability of their union is PA plus PB minus PA and B. And if they are mutually exclusive, we skip the minus part. If two events are independent, the probability of both happening is P of A times P of B. Conditional probability PA given B means the chance of A if B has already happened, and PA and B equals PA given B times PB. When events repeat independently, use multiplication for a chain and addition for alternative paths. Tree diagrams help visualize this. For independent events A1 to AN, the chance at least one happens is 1 minus the product of 1 minus each probability. That is, 1 minus the product of the quantities 1 minus pi. The total probability rule breaks a complex event into exclusive cases and sums their conditional probabilities times case probabilities. Bayes' rule reverses conditioning, letting us update probabilities when we see new evidence by using the total probability in the denominator. A probability distribution for a random variable lists possible values and their probabilities, which add to 1. And mean equals sum of xi pi, variance equals sum of xi squared pi minus mean squared. For a binomial experiment of n independent trials with success probability p, the chance of R successes is n choose R times p to the R times q to the n minus R, where q is 1 minus p. Some quick results. A fair coin tossed n times gives each sequence probability quantity 1 divided by 2 to the power n. And a fair die gives 1 divided by 6 to the power n for n rolls. When drawing cards, a standard deck has 52 cards, 4 suits, and known counts for face and honor cards that help compute probabilities. In random letter envelope match problems, the chance all letters are correctly placed is 1 divided by n factorial. And similar counting gives other cases. Let us now work through the solved examples to make ideas clear. Question number 1 asks, if cards are drawn without replacement, what is the probability a particular card appears at the nth draw? By symmetry, every card is equally likely at any position. So the probability equals 1 divided by 52, which is the answer. Question number 2 asks, 4 people each answer correctly with independent probability 1 divided by 6. What is the chance at least one is correct? The complement is that none answer correctly, which has probability the quantity 5 divided by 6 to the power 4. So the required probability is 1 minus the quantity 5 divided by 6 to the power 4. Question number 3 asks, drawing a card with replacement until a spade appears. Find the probability he fails exactly the first 2 times. Spade chance is 13 divided by 52 equals 1 quarter. Failure chance is 3 quarters. So failing first 2 and succeeding third has probability the quantity 3 quarters squared times 1 quarter, which equals 9 divided by 64. Question number 4 asks, from 9 people choose 5. What is the chance a married couple either serve together or not at all? Total ways are 9 choose 5 equals 126. Ways both serve are 7 choose 3 equals 35. Ways neither serve are 7 choose 5 equals 21. So favorable 35 plus 21 equals 56. Giving probability 56 divided by 126, which simplifies to 4 nines. Question number 5 gives biased die probabilities with phase 1 at 0.1 and phase 2 at 0.32 and asks, given either phase 1 or phase 2 showed, what is the chance it is phase 1? Use conditional probability. 0.1 divided by the sum 0.1 plus 0.32 equals 0.1 divided by 0.42, which simplifies to 5 divided by 21. Question number 6 asks to order PA and B, PA, PA or B, and PA plus PB in increasing order. So we note PA and B lesser than or equal to PA, lesser than or equal to PA or B, lesser than or equal to PA plus PB. Question number 7 picks an integer from 1 to 50 and asks some condition that comes out to 5 favorable numbers. So the probability is 5 divided by 50, which is 1 divided by 10. Question number 8 asks, with match win probability 1/2, what is the chance India's second win comes at the third test in a 5-match series? We need exactly 1 win in the first 2 and a win third. So 2 sequences, WLW and LWW, each with probability quantity 1 divided by 2 to the power 3, total 2 divided by 8 equals 1/4. Question number 9 has event probability 0.4 each trial for 3 independent trials. The chance at least one occurs is 1 minus the complement. 1 minus quantity 0.6 cubed equals 0.784. What do we learn from this? We learn the basic rules. Add for unions with correction, multiply for independent intersections, use complements for at least one, and use conditioning for dependent cases. Let us quickly remember, probabilities lie between 0 and 1. Complements add to 1, and tree and Venn diagrams help organize problems. Keep practicing these rules with cards, coins, and dice and solve problems step by step without skipping logic. Thanks for listening. Keep exploring more examples and notes on EduRev. And remember, every mistake is a step towards understanding.